Okay, to finish up the center of mass of the right cone, we start with the formula for the y center of mass. We slice this up into disks. That's a dm. The y is how far it is from here. dm is a volumetric density times a little volume. And the little volume of this disk is going to be the area at the top of the disk times how thick it is. That's the dy. So we're going to put our dm up here. And now we can see that r is going to be changing as we move up through y. We need to get rid of r. We can use similar triangles. R over y is proportional to capital R over capital H. Rearrange. Substitute for r up here, and here we have it. Square each term. Combine the y's, pull out the constants, and we're ready to integrate. And we have 1/4 y to the 4th. Putting in our limits, and our y becomes h. We can eliminate h squared, and it looks like we're almost done, except for one thing. What's the mass of the right cone? The mass will be the integral of all the little masses. Doesn't that look familiar? Density times the little volume. Same similar triangle idea. These are all constants. Integrate 1/3 y cubed. Put in the limits, and now we can reduce. I bet that looks familiar. There's the mass of a right cone. It's the density times the volume. Put the mass in for the mass. The y center of mass will not depend on the density. It won't even depend on how wide the cone is. I'm going to get 3/4 h. Good thing we only have a power of 1 here, because that is a distance, and that's what that should be. You think that makes sense? It's sure got to be more than halfway up.